Alright, so here's the thing. Throughout this entire Python tutorial, we're going to keep coming back to one problem, a parachutist falling from a hot air balloon. Now this might seem like a random example, but trust me, it's not. This is actually the central problem from your textbook, and it shows exactly why we need programming in the first place. So picture this. We have a parachutist. Let's say they weigh about 68 kilograms and they're about to jump from a hot air balloon that's just hovering in the air. The moment they jump, physics takes over. There are exactly two forces acting on them. First, gravity is pulling them down. That's just their weight, mass times g. And second, as they start falling, air resistance starts pushing back up. Now here's the interesting part. The drag force depends on how fast you're moving. The faster you fall, the harder the air pushes back. So at first, gravity wins and you accelerate. But as you speed up, drag catches up. Eventually, these two forces balance out perfectly and you stop accelerating. You've reached what we call terminal velocity. For our parachutist, that's about 53 meters per second. Okay, let's write this down mathematically. Remember Newton's second law from physics? Force equals mass times acceleration. Well, the total force on our parachutist is gravity minus drag. If we rearrange this a bit, we get something called a differential equation. Now don't worry if that sounds scary. It just means the equation tells us how velocity changes over time, not what the velocity actually is at any moment. See that dv dt? That's the rate of change. It says your acceleration right now depends on your velocity right now. The faster you're already going, the less you'll accelerate. Now for this particular equation, we're actually lucky. If you know calculus, you can solve this analytically, meaning you get a nice clean formula. You plug in any time t and boom, you get the exact velocity. For example, at t equals 10 seconds, our parachutist is falling at about 45 meters per second. Beautiful, right? Math just works. But here's where things get interesting. In real life, things are messy. What if the drag coefficient isn't constant? Maybe it changes with velocity. What if air density changes as you fall through different altitudes? And what if, and this is the big one, the parachute opens halfway down and suddenly your drag coefficient jumps from 12 to 68? For these realistic scenarios, there's no nice formula. Calculus can't save us. So what do? We turn to numerical methods. We let the computer approximate the answer step by step. This is where Euler's method comes in, and honestly, it's beautifully simple. Here's the key insight. Our differential equation tells us the slope of the velocity curve at any point. If I know my velocity right now, I can estimate what it'll be a moment later. It's just new velocity equals old velocity plus the slope times how much time has passed. That's it. That's the whole idea. Start at 0, take a small step forward, repeat. Let me show you what this looks like. The green curve here is the exact analytical solution, the one we got from calculus. And these red points, that's Euler's method in action, stepping forward every 2 seconds. See how it follows the curve? Not perfect, but pretty close. And if we made the time step smaller, it would be even more accurate. Look at the pattern here. Step 0, step 1, step 2. It's the same calculation over and over, just with different numbers each time. And that, my friends, is exactly what computers are designed to do. Repetitive calculations, that's their specialty. So by the end of this tutorial series, you'll know how to use variables to store all these parameters, loops to repeat the Euler step as many times as you want, lists to keep track of every velocity value, and functions to package everything into reusable code. You won't just learn Python, you'll actually understand how numerical methods work from the inside. Alright, let's get started.